Hi everyone, my name is Siddhesh Shinde and I'm a second year PhD student in the Department of Mechanical Engineering in the University of Michigan. And today I'll be talking about my research, which is to engineer hot cars in order to cool the planet. When I'm talking about cooling the planet, what I actually mean is addressing the issue of global warming. And in order to re emphasize the gravity of the situation that we are in today, I would like to show you a couple of images that were taken by satellites all over the Earth. This particular glacier in the Yosemite National Park is losing 3 feet of snow thickness every year. This lake in Iran occupies only 10% of the area it used to occupy in the 1970s. Polar bears are on the verge of extinction. There are certain species of penguins that are dying faster than ever before. And it's not just the wildlife that has been suffering. In the year 2003, 70,000 people all across Europe lost their lives to extreme heat waves. One of the major reasons for these effects that we see across the world is because of the massive amount of carbon dioxide that we are dumping in the atmosphere. And that will be pretty evident from this figure that I'll be showing you. On the x-axis, I have the history of the Earth in the past 600,000 years. On the y-axis is the amount of carbon dioxide in the Earth's atmosphere. Zero here represents the year 1950, and in 2014 we are right up there. So never before 1950 has the amount of carbon dioxide in the Earth's atmosphere crossed this line. So in some sense, we have literally crossed a line. It has been found that the single biggest contributor of carbon dioxide in the Earth's atmosphere is vehicular pollution. And in the United States alone, 27% of this carbon dioxide comes from vehicles. And this is the purpose of my research, to reduce the amount of emissions coming out of cars by reducing the aerodynamic drag. Now, this may sound a bit vague to you right now, but let's just start by understanding what aerodynamic drag means. In order to understand aerodynamic drag, let's go on a fun trip in a crowded New York subway. Hypothetically, let's assume that you're that guy and you want to move through a distance of 10 feet in this crowded train compartment. Now, in order to do that, it's obvious that you'll have to push people around, make your way through the crowd, and while doing that, you'll end up consuming a lot of energy. And the faster that you try to move, the harder it is going to get, and you'll need more energy to do that. So, in some sense, the existence of so many people around you will impede or resist your motion through the train. Now, something very much similar happens when you consider a vehicle moving on a freeway, because the air, as we know, is made up of these millions and millions of molecules. And the existence of these molecules resists the motion of the car. The faster the car tries to move, it consumes more energy, which means it consumes more fuel and therefore emits more carbon dioxide. So the resistance to the motion of any object when it moves through air is called as the aerodynamic drag. It turns out that the amount of aerodynamic drag any object experiences depends upon the pattern of airflow around that object. Now, in order to understand this better, let's consider an example of a golf ball. We all know that golf ball has these tiny dimples on its surface, and there is a very specific reason for that. The reason is to reduce the aerodynamic drag. Now, how does that work? Consider the motion of airflow around a smooth sphere like a ping pong ball, and that across the surface of a golf ball. Now, as we can see in these images on the left, which is a schematic, the airflow is attached to the surface of a golf ball for a larger distance as compared to that on a smooth sphere. On the right, I have images from an actual experiment, and it confirms the same fact that airflow is attached to the surface of a golf ball, which is dimpled for a larger distance as that compared to a smooth sphere. The point that I'm trying to make is later the flow separates from the surface of an object, lesser is the aerodynamic drag. Consider the airflow over surface of a vehicle moving on a freeway. It would look something like this. Now, because of this sudden change in the geometry near the rear end of the vehicle, the airflow which is initially attached to its surface, it suddenly separates and creates a massive region of separation near its rear end. Now, if only there was a way to keep the airflow attached on the rear end of the car as well, we would be able to reduce the aerodynamic drag. Now, it turns out that there is a way to do that, and the method is to introduce small obstacles on the roof of the car near its rear end. We call these obstacles as vortex generators in our research. Now, these small obstacles can be simple cubes, roughly that of the size of a dice, and it's an array of cubes, so a line of cubes which are placed on the roof near its rear end. And just because of the existence of these cubes on the roof of the car, the airflow remains attached to its rear end, therefore reducing aerodynamic drag. Now, while doing our research, we realized that cubes on the roof of a car would look hideous and no one would like to buy a car like that. Hence, the hope is that the final product would look something like this, which is cool enough and also reduces the amount of aerodynamic drag your car experiences. Some of the preliminary studies in this area have shown that we can reduce the drag on the car by around 8%. Now, it may not sound as a big number to you, but just imagine these vortex generators on the roof of every single car in the United States, and we can reduce the amount of CO2 emissions annually by 60 million tons. That is correct, 60 million tons. And that is a big amount and would make our Earth a lot happier than it is today.